Yeah. So hello everyone, and here we are going to present our project that we did this semester about the situational awareness using the monocular camera on the race car. So just to give an overview of our project, we developed vision-based navigation suite and deploys it for high-speed racing high-speed racing speed scenario, and so for the lane following, we use classical image processing techniques, and for the race car detection and position estimation, we used learning-based method along with the post estimation using the z-axis of the other race car.
Yeah, so for lane detection, as Sam introduced, we mostly use classic image processing techniques to isolate whatever we were trying to detect. So that would be the dash center line we see the image here, or the two lane boundaries on each side. And so the steps that we used for both of these scenarios include image cropping to isolate the region of interest, which is the bottom frame of the camera image frame, and then a Gaussian blur, erosion, and dilation to enlarge and make it so that filtering for the colors will perform better. And then an HSV filter. In the case of the center line, that would be a yellow HSV filter to isolate, to create a black and white image of the background and then the center line, as well as a bitwise end and a threshold to generate the final black and white image. After that, we use, not yet.
Oh, sorry.
After that, we use fine contours to generate the green bounding boxes we see. And then we use that to generate moments, which are basically centers of the contours, which we can use as waypoints for our race car to follow. And so, just one moment. Yeah, so lane detection the goal of our lane detection is to generate waypoints for our race car to follow. And so you can see in our image down here, we have two red waypoints that represent the waypoints for our robot to follow, for our race car to follow for either the left or right lane. And we went through two methods to generate these two waypoints. The image on the left shows bounding contours for the side white lanes as well as the center line, and those bounding contours were used to generate like an average lateral distance between the center and the side to get the exposition of the waypoints. And this performed pretty well for consistent light scenarios, light conditions. But when under testing, when our robot was in positions where it was, for example, facing the sun or facing large reflections from the ground, the white lanes would become harder to detect. And so we decided to go with the second method, which we see on the right, which simply uses the center line and then extrapolates two lanes to either side of the center line to generate the waypoints. So after creating the waypoint, we have a controller that takes the distance between the center of the car and the waypoint as our error term into our controller. And we follow an algorithm similar to that of the peer pursuit controller, which is basically a proportional control where the steering angle is proportional to the curvature of the arc, which is represented as y in the photo, y in the diagram, which is also the distance between the center of the image and the waypoint in the lane detection node, as I showed earlier. And so using this, we are able to output an Ackermann message to our lower level control, where our steering angle is determined by this proportional control, and our linear speed is just a constant speed right now. And so we have a demo video of lane following. And so right now this car is following. So we're going to see the race car follow this right lane all the way across the track for 2 laps, I think. And so the bottom frame shows the car running in the real world. The top 4 frames are recordings from the system. So the very top left frame is the lane detection node I showed earlier. And then with the waypoint that's following the red dot. And then the black and white image is the output from the color filters and the bitwise end. Yeah. So we are able to get pretty consistent lane following performance out of this, assuming that our lighting conditions are constant. So at different times of the day, we'll have to change the filters to get better responses. But if we're able to get if we're able to determine what time of day it is and then get the corresponding filters, we're able to pretty consistently follow the lane. Right now, the control method, because of the way it was designed, sometimes it likes to cut corners. You might have seen it earlier a little bit. It will cut the corner right here a little bit to the right. But that's something that could be worked on in the future. After this, we also did lane changing. So as I mentioned earlier, our lane detection node outputs 2 waypoints for the race car to follow. And so a simple matter of swapping which waypoint is output to the waypoint follower control will allow the robot to change lanes. So there's a small UI element. You might see where my mouse is moving in the video. There's a left and right button. And that's how I'm currently manually changing which lane to follow. So when I click the right button, it'll change to the right lane. And when mouse moves the left button and I click the left, and I click it, it will try to go to the left lane. Yeah, so these 2 videos are showing the same thing. We just ran it a couple times for the demo.
Yeah, and moving on to the race car detection and the position estimation. So first off, we got the model from Ziray, and we got the model working with the TensorRT using accelerated GPU programming on our Jetson board. And so the detection result was consistent in the indoor environment, but it was not too reliable in the outdoor environment, especially considering the data the data set used to train the model was exclusively taken in the indoor setting. And for after we got the bounding box from the model prediction, we estimated the position using the bounding box center. And just to recap, so without the scale factor, without the scale factor that we have for the depth for the depth image from the Z camera, the projected bounding box center from the pixel frame in the camera image to the word frame can lie anywhere along this line connecting the camera center and the actual bounding box center in the real world. So in order to get the correct estimate of the x and y coordinate of the bounding box center that we use to represent the other vehicle's position, we assume that the 2 race cars are on the same floor. So a single leveled floor, so we can use the prior knowledge of the height of the other race car to estimate its position on a 2D plane. So basically, it's saying the z-axis that we have, the z coordinate of the other race car with respect to our Eagle race car should be 0, assuming they are on the same level floor. So we can use that z coordinate to interpolate a coordinate along this line in order to get the actual x and y coordinate of the other race car. And so the estimated error currently can be anywhere between 0.1 to 0.3 meters in y and x, but that error mostly come from the manual measurement of the intrinsic transformations that we use to transform the point to the word frame, and the ground choose position, which we also measure by hand currently. Assuming we have an accurate extrinsic transformation and the ground choose position, the estimated error should be really small. And also considering the intrinsic parameters are accurate according to the Z camera factory calibration. So here's a visualization I created for visualizing the relative position of the other race car with respect to our Eagle race car. So here you can see the bounding box that's a little bit flickering. So it's present in some frames, but it's not in other frames. I'm thinking it's mostly due to the processing speed of the model prediction. So I think the time for the model to do one prediction is less than so it's more than one frame of the publishing rate. As you can see here, so the relative position from the visualization is mostly accurate, and it's according to what we have for the bounding box here. Yep.
And so the race car pose estimation node explained just now by Sam outputs a relative X and Y position of another race car that is detected by the camera. And using that, we can perform overtaking maneuvers if necessary. So the lane detection node I mentioned earlier is subscribed to the output of the race car position estimation. And we define a rectangular region right in front of the race car, which is the avoidance zone. So if we receive a relative X and Y location position for a race car that is inside of the rectangular region that we defined, we tell the race car to change lanes. And after this decision is made, there's a lockout period during which the race car cannot do this lane change maneuver again, so that we avoid the race car trying to repeatedly change lanes while it's in the process of doing the procedure. And after overtaking, we also switch back to the original lane after a couple of seconds for normal racing. So we have a couple demo videos to show this. Unfortunately, we were only able to get these indoors because, as mentioned earlier, our model was trained indoors, and we haven't had the chance to test this to create a model for the outdoors environment right now. But the right frame shows the robot performing the overtaking maneuver. The left frame, the bottom left frame, shows the output of the race car position. So the white dot represents the detection of a race car. The reason why the frame gets frozen is because when there isn't a bounding rectangle that is received from the model prediction, the frame just freezes. So when we see that video become active, it means that a race car has been detected. And so if that race car happens to be inside of the defined rectangular region, then our race car, the Eagle race car, will perform the overtaking maneuver. And so this also works for changing from right to left lane. So you see here. And this also works if the race car should not make overtake. So assuming the race car is on the other lane, our race car will not attempt to change lanes into that car because it's not inside of the defined rectangular region.
So yeah, as a conclusion, we combined the lane following and the lane switching algorithm with the classical CV techniques with the learning-based method to detect the other race car to perform the overtaking maneuver. And here are a couple future development that we are thinking about. So first one, to further increase the speed for lane following and switching, we should improve the control of the steering angle that we currently have. So what we currently have is just a proportional gain with respect to the arrow, but to make the traveling path smoother, we can try to deploy the PID control or more sophisticated model predictive control. And to improve the reliability of overtaking maneuver, there are two major factors that we can change. So first one is the extrinsic transformation. So to make the extrinsic transformation more accurate, we can perform a target-based extrinsic calibration method by using for example, aprotex to put aprotex around the room and let the vehicle travel around and take pictures, and using those to fit a transformation of the camera frame to the word frame. And also another factor is a model prediction results. And as you can see in the demonstration of the model prediction, so the first off, the model prediction is currently only reliable. It's only consistent in the indoor environment, and the bounding box can sometimes move around, and the prediction distance is not really long enough. So if the vehicle is for example like 3 meters away from our ego vehicle, the prediction model is not going to be able to predict it. That might be a limitation of the model or the limitation of the image resolution. But to improve the model prediction results, we can use a different model structure. Since Ziray wrote this model 2 years ago, and during these 2 years, there are new model structures that's coming out for better prediction results, for better prediction performance. So a few of them are a YOLO V3 and fast Mask-R CNN, but that's for but Mask-R CNN is for the image segmentation. But I think we can use the segmentation result just the same. And furthermore, we can we can collect more data and label the data in both the indoor and outdoor environment to retrain the model to make the model more accurate. And last but not least, we should switch the dead camera to pi camera, just for having multiple cameras on the race car in the future. And with that, we conclude our presentation for our project.